In this video, I want to do a couple of examples of finding higher order derivatives using implicit differentiation. In this example, we need to find the second derivative of x plus y squared equals 1. To find the second derivative, we have to find the first derivative first. The derivative of the first term, x, with respect to x, is 1. And the derivative of the second term on the left, y squared, is 2y dy over dx. And that's equal to the derivative of the constant 1 on the right, which is 0. Now let's solve this equation for dy over dx, because dy over dx is the first derivative. Subtracting 1 from both sides gives us this equation. And then dividing both sides by 2y gives us dy over dx equals negative 1 over 2y. And that is the first derivative. Now we'll use the first derivative to find the second derivative. The first thing I'm going to do is rewrite the first derivative as negative 1/2 times y to the negative 1, because this is going to make finding the second derivative easier. To find the second derivative, we have to use the chain rule. The derivative of the outside function, or the entire function, is 1/2 times y to the negative 2 power. And the derivative of the inside function, y, is dy over dx. And what we notice here is that our second derivative is stated in terms of our first derivative. In other words, the second derivative contains the first derivative. The first derivative is dy over dx. We've already found the first derivative, dy over dx. It's negative 1 over 2y. So wherever we see dy over dx in the description of our second derivative, we're going to back substitute in the value of the first derivative, negative 1 over 2y. Now, to make simplifying this expression a little bit easier, let's take the y to the negative 2 and make that exponent positive. And multiplying the two fractions gives us negative 1 over 4y to the third. And that's our second derivative. In this example, again, we're asked to find the second derivative of e to the 2y plus x equals y. Let's start by finding the first derivative. The derivative of the first term, e to the 2y, is e to the 2y times 2 dy over dx, and that's using the chain rule. The derivative of x with respect to x is 1, and on the right, the derivative of y with respect to x is dy over dx. Now let's simplify the left side just a little bit. Multiplying e to the 2y times 2 dy over dx gives us 2e raised to the 2y dy over dx plus 1 equals dy over dx. Now let's manipulate this equation to get both of the terms that contain dy over dx on the same side. So I'm going to subtract dy over dx from both sides and 1 from both sides of this equation. That moves the dy over dx to the left side and the 1 to the right side of this equation. Now let's factor out dy over dx from both terms on the left. And that gives us this equation. Now, to solve for dy over dx, the first derivative, we'll divide both sides of the equation by the difference 2 times e to the 2y minus 1. And there's our first derivative. Now I'm going to distribute the negative in the numerator of this fraction into the denominator, just to make our lives a little bit simpler. And that gives us 1 over 1 minus 2 times e to the 2y. And I'm going to simplify this one step further so that we don't have to use the quotient rule when finding the second derivative. So I'm going to rewrite 1 over 1 minus 2 times e raised to the 2y as 1 minus 2 times e raised to the 2y raised to the negative 1. Now let's begin the process of finding the second derivative. To find the second derivative, we'll have to use the chain rule. The first thing we need is the derivative of the entire outside function, or the entire first derivative. Using the power rule, the derivative of the outside is the opposite of the difference 1 minus 2 times e raised to the 2y raised to the negative 2 power. Now we multiply that by the derivative of the inside. The derivative of the first term on the inside, 1, is 0. And to find the derivative of the second term, negative 2 times e raised to the 2y, we have to use the chain rule again. The derivative of that entire expression, negative 2 times e raised to the 2y, is negative 2 times e raised to the 2y. And we multiply that by the derivative of the inside function, or in this case, the exponent of e. The exponent of e is 2y, and the derivative of 2y with respect to x is 2 dy over dx. Now we can start simplifying this monstrous expression. I notice that we have a negative times a negative 2 times a 2. That gives us positive 4. And that's multiplied by e raised to the 2y and dy over dx. So far we have 4 times e to the 2y times dy over dx. And that's still multiplied by the difference 1 minus 2 times e to the 2y, all raised to the negative 2 power. But I'm going to manipulate this in such a way that we make that negative 2 exponent a positive 2 exponent. So that places the difference 1 minus 2 times e raised to the 2y in the denominator of a fraction, and the negative 2 exponent now becomes a positive 2. Now wherever we see dy over dx, we'll substitute in the value of the first derivative. The value of the first derivative is 1 minus 2 times e to the 2y, all raised to the negative 1 power. Making that substitution gives us this expression. Now I notice that I have factors of 1 minus 2 times e raised to the 2y power in the numerator and denominator. So I'm going to move the factor in the numerator into the denominator to make the negative 1 exponent a positive 1 exponent. Doing that gives us this expression. Now let's multiply the like bases in the denominator together. And finally, that gives us our second derivative. 4 times e raised to the 2y over the quantity 1 minus 2 times e raised to the 2y to the third power.